Hello, welcome to Introduction to Composites. This is the fourth day of the ongoing week. Yesterday we learnt the relationships between stress and strain in context of an orthotropic lamina which was loaded in such a way that the external loads were aligned to the material axis of the system, and this was the case of general orthotropy. And what we had seen was that in this kind of a situation, the stress strain relationships are such that purely extensional stresses create only extensional strains and vice versa, and the presence of a shear stress generates only shear strains. And we had also mentioned that there are 4 independent elastic constants for such a material, and those are EL, that is the Young's modulus of the material, not the Young's modulus, the elastic modulus of the material in the longitudinal direction, ET, which is modulus of the material in transverse direction, the shear modulus GLT, and the Poisson's ratio nu LT, which is major Poisson's ratio. So, now what we will do is we will quickly do an example and then we will move on to the case of general orthotropy. So, example, so the problem is that we have a lamina, fibers are oriented in this direction, and I am loading it in such a way that sigma L is equal to 3 MPa. It also has transverse load such that the transverse stress sigma T is equal to 0.5 MPa, and then there is a shear stress and the shear stress equals 3.5 MPa. So, this is the stress state of the lamina, and the material properties of the lamina are such that EL is equal to 14,000, ET equals 3,500, GLT equals 4,200, nu LT equals 0.4, and nu TL, which is not independent, we can actually calculate it, but here we are just given the value, and that is equal to 0.1, and these first 3 entities EL, ET, GLT, they are in megapascals. So, the question is calculate. So, what do we have to find? So, we have to find epsilon L, epsilon T, and gamma LT. So, we start doing this. So, epsilon L equals sigma L over EL minus nu TL times sigma T over ET, and if I plug in the values, what I get is 200 into 10 to the power of minus 6, and the units of strain are dimensionless, so it is just that number. Then we have epsilon T equals minus LT sigma L over EL plus sigma T over ET, and once I do all the calculations, I get this as 57 times 10 to the power of minus 6 microstrains, and finally the shear strain is tau LT over GLT, and that works out to be 833 microstrains. So, these are the strains. So, this is how we calculate strains in a especially orthotropic lamina. Next, we will move to generally orthotropic lamina. Generally orthotropic lamina, and here the reference system and the convention for the angle is important. So, here we have the material sample such that its fibers are oriented like this. Okay. So, my L direction, this is L direction, this is T direction, and then my X direction is this and Y direction is this, okay, and this angle is theta. So, theta is the angle between X and L going upwards in the counterclockwise direction. And this plate can be loaded by sigma x it can also be loaded by sigma y, and it can also see some shear stress. So, that is tau x y, and again note the direction of tau x y, this is positive tau x y. So, sigma x is positive, sigma y is positive, and tau x y is also positive. This is how our sign convention is assumed to be. So, for this kind of a situation, what we will do is we will write down relations between, so we will develop relations between stresses. So, what are the stresses? Sigma x, sigma y, tau x y, and strains epsilon x, epsilon y, gamma x y. Okay. This is what we will develop. So, again we will have 4 different cases. Case 1, in the first case we have only sigma x. So, sigma x is not equal to 0, sigma y and tau x y are 0. Now, this is the case of general orthotropy. So, when I am pulling the material, it will not only exhibit extensional strains, but it will also exhibit shear strains. So, we will write down the relationship between stresses and strains. So, epsilon x is sigma x by E x, where E x is the modulus of the material, extensional modulus of the material in x direction. Epsilon y, so when I pull it, it will also become slimmer, and so the Poisson, so it will exhibit Poisson strain. And what is Poisson strain? Minus nu x y, first index x which indicates the direction of the external load, second index y which indicates the direction of the extensional strain. So, nu x y times sigma x by E x, because this is nothing but epsilon x, okay, and it will also exhibit a shear strain. So, it will also exhibit shear strain, and that we define as one constant minus mx times sigma x by EL, okay. sigma x by EL. So, this is the first case. Case 2, so in case 2 we have sigma x is equal to 0 and the same thing is true for tau xy. The only thing which is non-zero is sigma y is not equal to 0. So, epsilon y, so I am pulling it in the y direction. So, first thing is sigma epsilon y will be sigma y divided by Ey, then epsilon x will be there because of Poisson's effect, and that will be equal to negative Poisson's ratio mu yx times the strain in the y direction. And what is the strain in the y direction? Sigma y by Ey. And there will also be a shear strain gamma xy, and gamma xy will be equal to minus my sigma y divided by EL. So, this is the second case. So, again if you double the external stress, the strain will double because this is linear elasticity. So, this is the second case. The third case is sigma x equals sigma y equals 0 and tau xy is not equal to 0. And in this case the shear stress will first it will generate a shear strain, and what is the value of that shear strain? Gamma xy is equal to tau xy divided by g xy. And as I said, it also will generate extensional strains. So, it will generate epsilon x, and that is equal to, when we observe it, we find, and this we will later prove these relations, this is equal to minus mx tau xy divided by EL, and epsilon y equals minus my tau xy divided by EL. These mx and my are called cross coefficients. Because they couple the extensional and the shear responses of the system. So, they connect the stress in longitudinal direction or transverse direction to shear strain, and they also connect the shear stress to strains in x and y direction. So, that is why they are known as cross coefficients. Now, here we have how many elastic constants we have? We have elastic constant Ex, Ey, nu xy, nu yx, mx, my, gxy. So, we have 1, 2, 3, 4, 5, 6, 7 elastic constants, but we will later see that they are not necessarily mutually independent. We can express all these elastic constants in terms of the 4 fundamental elastic constants which we had discussed and defined when we were discussing a special orthotropic case. This is something we will explain. If we will probably start today and then we will certainly do it tomorrow. We will express these constants in terms of EL 4 independent elastic constants. So, these Ex, Ey, mu xy, mu yx, mx, my, gxy is just functions of those basic 4 elastic constants for especially orthotropic plate. So, these are the 3 cases when we apply only one stress, and if we apply all the stresses together, that could be case 4. And how do we develop the strain stress relationships? Basically through the principle of superposition. So, here sigma x is not equal to 0, sigma y is not equal to 0, tau xy is not equal to 0. And through principle of superposition, we just add up the contributions from each of the stresses. So, we get this relation. So, epsilon x is epsilon x will have one component due to sigma x, one component due to sigma y, and one component due to tau xy. So, the component due to sigma x, so here we will have a vector sigma x, sigma y, and tau xy, and the coefficient associated with sigma x is 1 over E x, and then the coefficient associated with y is minus nu y x divided by E y, and then this is minus m x by E L, and then the second row we have minus nu x y divided by E x 1 over E y and minus m y divided by E L, and then we have m x divided by E L minus m y divided by E L, and lastly we have 1 over G x y. So, these are the relations, and this we are getting just as we got the relation in the case of special orthotropy, these relations by principle of superposition. Similarly, we have used the same approach to develop stress strain relationship for a generally orthotropic lamina when it is subjected to all the three stresses sigma x, sigma y, and tau xy. Okay. So, this is where we are. The next thing is, so now we have the relations for special orthotropic lamina and generally orthotropic lamina. So, then the next question is, what is the relationship between E x, E y, G x y, nu x y, nu y x, m x, m y. This is for, and how can we express these terms, these things in terms of E L, G L T, E T, nu L T, which are 4 fundamental constants, elastic constants for a especially orthotropic lamina. So, this is our next thing, and this is exactly what we will start discussing tomorrow, and till then I hope you have a great day, and we will meet once again tomorrow. Thank you.